So, dear students, in this video, we will further take on this the advantages of advantages of making use of negative feedback to an amplifier, and one of the important implications of negative feedback to an amplifier is that we can enhance, we can increase the input resistance of an amplifier, or effectively talking input impedance. So if we go back to the feedback system, we have uh, we have an amplifier, and let us assume that this amplifier has a gain equal to A, and then we will have the output from this amplifier. It has input, and and we have a feedback circuit. So suppose let us suppose that Vi is the input voltage. Here we will have V out, and a part of this V out will be subjected to the feedback circuit, and and the so this is my feedback circuit, and let us suppose that the feedback ratio here is beta. So this is the simplest way of drawing a block diagram of feedback amplifiers. And here we are talking about negative feedback, and we better understand that if I have an input signal of some magnitude, and suppose I use an amplifier with common base configuration. Here I'll have an amplified signal, and this signal will be subjected to the feedback circuit, and from here, so here V out will be, because V out by Vi should be A, so that implies this V out should be AVI. So when this output voltage is subjected to the feedback circuit, here we have beta. So here we'll get an output, and that output will be VF, and that VF will be beta V out, but V out is A VI, so it must be beta A VI. So this can be the situation here, and what's our aim here is, basically is we want to see that we are, when we are making use of negative feedback to the amplifier, what happens to the input impedance. So I'll go with with defining the input impedance, and for that, let us suppose that Zi is the input impedance, and this Zi is the ratio between voltage and current, and and so this should be my input impedance in absence of negative feedback. So that should be the case. And then I would like to define the input impedance Zi dash, and this Zi dash will be the ratio between the signal voltage and 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 I. Okay, so that should be the case here. So this Zi dash will refer to the same thing, but in presence of negative feedback. That should be the case here. Now, if we go back to our situation, we can define that once there is once there is a loop gain in the given system, we can write down Vi equals Vs minus Vf. All right, so that should be the case. Uh, so this Vf is already defined, and this Vf is basically beta V out. But when we subject it back to the feedback circuit, we can write this Vf as A beta Vi. So it should be something like this. Uh, okay, sorry. This is V. Uh, this is V out here. This is V out here equals beta Vi. Okay, so finally Vf will be A is the voltage gain, beta is the feedback ratio, and Vi is the input voltage. So if I go with this kind of situation, I'll write Vi is Vs minus A beta Vi. So I can turn down this to the left hand side. This is Vi minus A beta Vi equals Vs. So from here we can write here plus because we have to transform it. So then this implies my Vs will be Vi times 1 plus A beta. Now this is my Vs, which I have obtained from this equation, and I can make use of this Vs in Zi dash in this equation. So let's do that and see what's the result that we obtain from here. So by doing that, so what will we get is Zi dash, that is Vs, but Vs is Vi times 1 plus A beta divided by I. Now, what is the ratio between Vi and II? It's already defined as Zi. So what's going to happen here is that Zi dash will be Zi times 1 plus A beta. That means the the input impedance of the amplifier is going to increase when we are making use of negative feedback to the amplifier. So this thing should be clear. So here I would say that this Zi dash is greater than Zi. So certainly we can see here that the negative feedback that we have used for this amplifier in common base configuration, it certainly increases the input impedance of the amplifier. On similar considerations, when you will mark same calculations and mark some symbols to the same block diagram that I have talked about, in that case, certainly you are going to, if you make use of same analysis for output output impedance, what you are going to obtain here is you are going to obtain Z out dash equals Z out divide by 1 plus A beta. So here, when you'll do the same kind of analysis, you'll take care of the symbols and you'll take care of the region where you are trying to calculate this output impedance. So what you will obtain is that the output impedance will be output impedance in presence of feedback will be output impedance in absence of feedback divide by some number. So that certainly implies that this Z O dash will be less than ZO. So that means in this case, the impedance is going to decrease, which is ideally good, which is ideally beautiful for an amplifier to have a large impedance, input impedance, and to have small output impedance. And we can mark the similar kind of analysis for other factors, and we'll come up with results like the results that we have obtained for impedance, for distortions, and for other factors. I mean, if you will do same analysis for noise, so what will happen in that case? For noise, you will have decrease in noise. So you will have you can you if your input signal is accommodated by some kind of noise, that noise can also be reduced by making use of negative feedback. In that case, if I define the amplitude of noise in presence of feedback as V dash and amplitude of noise in absence of feedback as Vn, the result under same circumstances will look like Vn dash is Vn divide by 1 plus a beta. So here you can see that by making use of negative feedback to the circuit, you are certainly going to decrease the magnitude of noise by making use of negative feedback in the circuit. So negative feedback leads to decreased magnitude of noise. Okay, so here I would like to end this video.